All right, in this video, we're going to talk about one of the specific types of solution by substitution called a homogeneous differential equation. A homogeneous differential equation will be such that if we substitute tx for x and ty for y, that a common factor of t to the n will factor out of everything in front of the original expression f of xy, and that will tell us that every term is the same degree, and this will be homogeneous degree n. When we make these substitutions, it's possible that we get any of the kinds of differential equations that we've talked about so far. We've talked about separable, linear, and exact differential equations. All of the examples that I'm going to work right now are going to be separable differential equations. That does not mean that it will always work out that way, but many times they will turn out to be separable differential equations. That should be the first thing that you're looking for. If you can't make it separable, then check to make sure that it isn't linear. There are two substitutions that we can make here in this case. We can either use the substitution y equals ux, or we can use the substitution x equals vy. Your teacher may write these a little differently, but this is usually how the textbook talks about these. And so if we have this substitution, that means that dy dx is going to be u plus x du dx because of the chain rule, or dy is equal to u dx plus x du. And when we come back and make our substitution for u at the end of the problem, u is going to be y over x. Here we have dx dy is going to be v plus y dv dx. So dx will be equal to v dy plus y dv. And when we come back and make our substitution at the end of the problem, v will be x over y. Let's look at some examples here. First example will be x minus y dx plus x dy is equal to 0. One other note, we're going to use the word homogeneous later to mean something completely different. This is one of the ways in which the word homogeneous is meant, and you need to say it's a homogeneous differential equation of degree whatever here to be exact in what you're talking about, as opposed to later when we talk about linear differential equations of higher, especially of higher order. When we say that it's homogeneous, will mean that the right-hand side is equal to 0, that we have a linear differential equation of degree whatever, and that is homogeneous, meaning that it's equal to 0. So don't get this confused with that when I say homogeneous differential equations. This is not linear homogeneous differential equations yet. All right, so let's see. To figure out which substitution we should make, we usually look for where the monomial term is here and try and let that differential be what we make the substitution here, so that we only have one thing times this binomial here instead of a binomial times a binomial here. When we get a choice about it, let's make the substitution that way. So we want a dy. So we're going to choose y equals ux. So x minus ux dx plus x times u dx plus x du is equal to 0. And let's just distribute everything now. X dx minus ux dx plus ux dx plus x squared du is equal to 0. And these two terms are equal and opposite, so they zero each other out. Now I can separate what's left and get x dx is equal to a negative x squared du. So negative 1 over x dx is equal to du. Let's go ahead now and integrate both sides. And let's actually leave the negative over here. X dx, let's make that a negative du on that side. So when we integrate both sides here, I have ln of the absolute value of x is equal to a negative u plus c. So I'm going to make this ln of the absolute value of x plus u is equal to c. Let's make my substitution back that u is y over x. The absolute value of x plus y over x is equal to c. And then we'll multiply both sides by x to get rid of that fraction there. So this is going to be y plus x ln of the absolute value of x is equal to cx. All right. Let's look at the next problem here. X dx plus y minus 2x dy equals 0. You can see that the monomial term here is with the dx, so I'm going to let x equal v y. Dx is going to be v dy plus y dv. And so we have vy times v dy plus y dv is equal to, oops, I'm sorry, plus y minus 2vy equals 0, vy dy. And so we have v squared y dy plus vy squared dv plus y dy minus 2vy dy is equal to 0. And we're going to get our dy terms over here by themselves and the dv terms on the other side. So we'll say equals a negative vy squared dv. Get that to the other side. Now we have a v squared y term and a minus 2 vy term and a plus y term dy. I see a common factor of y on the left-hand side that I'm going to pull out, make v squared minus 2v plus 1 dy is equal to a negative vy squared dv. And I can further factor this since it's a perfect square. V minus 1 squared dy equals negative vy squared dv. Let's separate this now and get my y's on the left with my dy and my v's on the right with dv. So y divided by y squared is 1 over y dy is equal to a negative v over v minus 1 squared dv. So I have some options here that I can let's just go ahead and add and subtract 1, because that's going to split this up nicely. Instead of doing partial fraction decomposition, I'll just add 1 and subtract 1. And when I do that and pull the -1 out, I'll have a v minus 1 on the top that will cancel. So I'm going to make this 1 over y dy is equal to a negative v minus 1 over v minus 1 squared minus 1 over v minus 1 squared. This is dv dv, and 1 over v minus 1. So ln of the absolute value of y equals negative ln of the absolute value of v minus 1 minus, and then this is going to be a -1 over v minus 1. So that's multiplied by that -1. It's going to be plus 1 over v minus 1, and then plus c. You could also use partial fraction decomposition here if you wanted to solve for those numerators to figure out how this would break up here. And so I'm going to bring these logs together over here and make this ln of the absolute value of y times v minus 1 equal to 1 over v minus 1 plus c. And then v is x over y. So ln of y times x over y minus 1 equals 1 over x over y minus 1 plus c is going to be ln of the absolute value of x minus y equals, and I'm going to multiply by y over y here, y over x minus y plus c. And then I'm going to multiply by that denominator there of x minus y across everything to get rid of the fraction. X minus y, ln of the absolute value of x minus y is equal to y plus c times x minus y. Next problem here is going to be y squared plus yx dx minus x squared dy equals 0. And so let's let y equal to ux. And we have u squared x squared plus ux squared dx minus x squared times u dx plus x du equals 0. U squared x squared dx plus ux squared dx minus ux squared dx minus x cubed du equals 0. Ux squared dx and negative ux squared dx zero each other out. I'm going to separate these. U squared x squared dx is equal to x cubed du. Separating 1 over x dx is equal to 1 over u squared du. We'll integrate both sides here. Ln of the absolute value of x is equal to negative 1 over u plus c. So this is going to be ln of the absolute value of x is equal to a negative. The reciprocal of y over x is x over y plus c. Let's multiply everything by that y in the denominator, and we'll make this y ln of the absolute value of x equals negative x plus cy, and then bring this term over to make this x plus y ln of the absolute value of x is equal to cy. All right, let's look at number 7. Number 7 is dy dx is equal to y minus x over y plus x. And I'm just going to go ahead and make this y plus x dy equals y minus x dx. And there's no advantage to either substitution here because we're going to have binomial times binomial no matter what. So I'm just going to let y equal ux here. And that's going to be ux plus x times u dx plus x du is equal to ux minus x dx. This is going to be u squared x dx plus ux squared du plus ux dx plus x squared du is going to be equal to a ux dx minus x dx. So ux dx on both sides zero each other out. And then that's going to leave me with my, let's leave my du's on the left and my, bring my dx's to the right. So this will be ux squared plus x squared du is equal to a negative u squared x minus x dx. So that's going to be x squared times u plus 1 du is equal to a negative x times u squared plus 1 dx. So we're going to make this u plus 1 over u squared plus 1 du is equal to a negative 1 over x dx. Let's split that 1 on the left into two integrals. I see two different rules at play there. So u over u squared plus 1 over u squared plus 1 du on both of these. Right here equal to integral of negative 1 over x dx. So this is 2 and 1/2 makes 1/2 ln of the absolute value of u squared plus 1 plus arctangent of u equals negative ln of x plus c. And so that's going to be 1/2 ln of absolute value y squared over x squared plus 1 plus arctangent of y over x plus ln of the absolute value of x here is equal to c. And then let's go ahead and make this 1/2 ln of y squared plus x squared over x squared plus arctangent of y over x plus ln of the the absolute value of x equals c. Move this a little bit more. 1/2 ln the absolute value of y squared plus x squared minus 1/2 ln of the absolute value of x squared. That 2 comes down with that 1/2 and cancels it out, plus arctangent y over x plus ln of the absolute value of x equals c. So we have 1/2 ln of, and these are both squared, so I don't need absolute value bars anymore because they're always going to be positive, minus ln of the absolute value of x plus arctangent y over x plus ln of the absolute value of x equals c. This and this zero each other out. I'd like to get rid of that 1/2, so we'll call these things here c1 and multiply by 2 ln of x squared plus y squared minus, plus 2 arctangent of y over x is equal to 2c1, which is going to be c2, which I'll just call c in my final answer. That was number 7, I believe. Yes. So let's look at number 9 now. Negative y dx plus the quantity x plus square root of xy dy equals 0, like that. And so I think that it's going to be easier to find dx here times this monomial. So I'm going to let x be equal to vy. Dx is going to be v dy plus y dv. So we have a negative vy times v dy plus y dv plus quantity vy plus square root x is vy, so I have a vy squared here. Dy equals 0. I have a negative v squared y dy minus vy squared dv plus vy dy plus y square root of v dy, and that equals 0. So this is negative y. That wasn't an x, that was a negative y. So this is negative vy dy minus y squared dv. There we go. So negative vy dy and positive vy dy zero each other out. And I'm left with negative y squared dv plus y root v dy equals 0. I'm going to separate these. So y root v dy equals y squared dv, and 1 over y dy equals, and I'll just write this as v to the negative 1/2 dv. So the ln of the absolute value of y is equal to 2v to the 1/2 plus c. So ln of the absolute value of y is equal to 2 square root of x over y plus c. And I'm going to take the c over here. And then I'm going to square both sides. Switch sides when I do this. 4x over y is equal to ln of the absolute value of y minus c quantity squared. So 4x is equal to y times ln of the absolute value of y minus c quantity squared. Let's do one initial value problem here to wrap up. That is based off of this, x y squared dy dx is equal to y cubed minus x cubed. And we're told that y of 1 is going to be equal to 2. I see a dy dx in this problem, so that tells me that I probably have let y equal ux. Dy dx is going to be u plus x du dx. So let's make this substitution here. X times ux quantity squared times u plus x du dx is equal to ux cubed minus x cubed. So x times u squared x squared, so u plus x du dx is equal to u cubed x cubed minus x cubed, and that is u squared x cubed times u plus x du dx is equal to u cubed x cubed minus x cubed. So I'm going to divide everything here by u squared x cubed. That gives me u plus x du dx is equal to 1 over u minus 1 over u squared. I'm sorry, this is just regular old u. That's a u cubed over u squared is u. So u is on both sides of the equation and we'll zero each other out. X du dx is equal to a negative 1 over u squared. So this is going to be u squared du is equal to a negative 1 over x dx. Make this 1/3 u cubed is equal to a negative ln of the absolute value of x plus c. Let's go ahead and make our substitution here. Y cubed over x cubed is plus ln of the absolute value of x is equal to c. And let's make our substitution now. We're using the point 1, 2. So when x is 1 and y is 2, 1/3 of 8 over 1 plus ln of 1 is equal to c. 8/3 is equal to c. So we have 1/3 y cubed over x cubed plus ln of the absolute value of x is equal to 8/3. Let's multiply everything by 3 to get rid of those fractions. Y cubed over x cubed plus ln of the absolute value of x is equal to 8. And then we'll multiply by that x cubed as well to get rid of the fractions. Y cubed plus x cubed ln of the absolute value of x. This is 3 of these. is equal to 8x cubed. And that's our final answer. And that's it for this video. We'll come back next time and we'll talk about another type of solution by substitution, which is going to be a Bernoulli differential equation. See you for the next video.